So that's a magnesium 2 plus 8. That's how the book writes it, because now it's allowed to, it's told us what.
And right next to it, Professor, and also sodium
and
exported?
also sodium is exported against a concentration gradient.
Okay.
Because, so I'm going to make a little loop that this is what, sorry. Oh, this is all talking about the sodium potassium pump. That the sodium potassium pump spends ATP to import potassium against a concentration gradient and to export sodium against a concentration gradient. It spends energy to maintain the concentrations needed for life in the cell. So there is a picture of this, and it's a little more detailed than, I don't care that you know the ratio of, 3 sodium to 2 potassium. You guys learned that before, and that's okay. I just want the idea behind the gradient, because when you go into 415, the gradient is, and the relative concentrations are super important. So, let's look at that. Oh, it's flashing.
So the cell won't work if there's an equal balance of sodium and potassium?
It doesn't work. Our physiology has evolved to require a high concentration of potassium in the cell. And so if we don't maintain that, the cell won't work.
And that's the desired look for...
So in a system, just in a, if you put, so in 100B, we do this experiment with dialysis tubing. In most things in our existence, the kidney, the intestine, anything that we talk about diffusion across the semi-permeable membrane, this is how this works. So what we do in 100B is we put dialysis tubing in a bag, and you may have done this in 353, I don't know. And we put a couple of different substances inside the bag and outside the bag. And the substances inside the bag, one is small and one is big. And the substances outside the bag, one is big and one is small. So we see, and that the dialysis tubing is semi-permeable, meaning that the holes are very, very small. So if it's a really small thing, like we put iodide, potassium iodide, I2KI, we put that outside because it's a small molecule, and we can watch it diffuse into the bag. And what that means is it starts out really dark outside the bag, and the bag starts clear. By the end of the experiment, half of that iodide, potassium iodide, has moved into the bag because the molecules are small enough that they can pass through the holes in the dialysis bag, and they want to be there. They want to be there because just based on the biology or the entropy or anything you want to think about our universe, this is just how we tend to be. We tend to move from an area of high concentration to low concentration to establish equilibrium. I don't know enough base level physics to explain adequately why that is. Molecules just do that. So, I mean, there's some sort of quantum mechanic thing that explains it, but I can't do it. So by doing that experiment, you can also see that when you put starch inside the bag, the starch is too big. So starch, I think we use amylopectin, and it's this big molecule and it's cloudy. So we put amylopectin inside the bag. So if the molecules were big enough were small enough to move through the holes in the dialysis tubing, the water would become cloudier outside the bag and clearer inside the bag because half of the starch would move from inside to outside. What happens is the holes are too small, the molecule's too big, and it stays cloudy inside the bag and it stays clear outside the bag. And that's just because of the way that the universe runs. I would love to have a better explanation, but I don't. And I'm sure there's some giant equation for it, but I don't have that either. I can find it and bring it in, but that's just what we do in the universe. So everything from, this is how the kidney works, because when you go through the kidney, we talk all about how we take it back in. There's a point where we shove it all out into the fluid, and then some of it we take back and some of it we don't take back. And that's the idea behind the dialysis tubing. Some of it is just based on relative concentrations. If we have a higher concentration in rather than out, we don't take it back because we have too much. If we have a higher concentration out rather than in, we take it back because we need it. So this is the base state idea of how that works. We use the sodium-potassium pump and other energy-dependent mechanisms to work against the natural order. That's why we do it. We spend the energy only because we need this to function. Otherwise, we wouldn't spend the energy. So, in the context of sodium, potassium, and chloride, Potassium is the largest intracellular cation. Sodium is the largest extracellular cation. That's, I'm sure I have that written somewhere, but it's really important. So the largest single fraction